In this video, we're going to talk about the titration curves of a strong acid and a strong base. So in this case, we're going to use the same example as we had last time, where we have HCl as our analyte. So down here we have a beaker of HCl. We don't know the concentration of it. In our burette, we have NaOH. We do know the concentration of that. And we're going to set this up. So in this case, what we're going to do is we're going to set up our titration, and inside the HCl, we're going to put a pH probe. And that's just going to allow us to measure our pH. And so what you're going to do is you're going to kind of add NaOH slowly, measure the pH with the pH probe, and then we're going to plot that as a function of, the pH is a function of the volume of titrant added. And we're going to get this graph that we see here. And this is what we call the titration curve. So what's happening is we add the NaOH and it reacts with the HCl to make NaCl and water. And we know that because this is a strong acid and a strong base. So these are going to neutralize each other to form a neutral salt. So if you don't remember why NaCl is a neutral salt, you should go back and you should watch the video on salts and hydrolysis and water. And so that's going to be what's sort of happening as we add the NaOH. Now, the first thing I'm going to point out is, well, where is the equivalence point on this? And so let's think about what happens when we get to the equivalence point. So when we get to the equivalence point, our moles of HCl and our moles of NaOH are going to be the same, meaning we're not going to have a particular limiting reagent anymore. So when we get to the equivalence point, let's say, for example, we have 1 mole of HCl and we have 1 mole of NaOH. So at the equivalence point, we're going to have added, let's just say we have 1 mole of HCl. So at the equivalence point, we're going to need 1 mole of NaOH. That's how I knew before I even wrote it down that it was going to be 1 mole, because they're equivalent. So when this happens, so when we start, and this is going to be we're going to kind of simulate a stoichiometry table here. So when we get to the equivalence point, we're going to have 1 mole of NaOH and 1 mole of HCl. So there is not going to be a limiting reagent at this point because they're equal. So they're going to equal each other. So we get minus 1 mole, we get minus 1 mole. We're going to get 0 moles of HCl. We're going to get 0 moles of NaOH. And we're going to get plus 1 mole of NaCl. So all we're going to have in solution at the equivalence point is we're going to have NaCl and water. And so if we have NaCl, which is a neutral salt, and water, our pH has got to equal 7. So at the equivalence point, our pH is going to equal 7 with a strong acid and a strong base. And if you look where pH 7 is, it's in the middle of this rapid rise. And that makes a lot of sense. We're going to talk about why that makes a lot of sense in a few minutes. But whenever you have this rapid rise, the inflection point in that rapid rise is the equivalence point. So I could have actually looked at this graph, figured out the inflection point by taking the derivative, or the second derivative, and wherever that second derivative goes to 0, which is where you get an inflection point in calculus, that's going to be where your equivalence point is. So we're going to call this point B. And that's going to be my equivalence point. And the pH at that point is going to be equal to 7 because the strong acid and the strong base makes NaCl and water, which are both neutral. Okay, so we figured out where our equivalence point is on this graph. Now let's look at what happens when we go from sort of this area A, where we have basically no titrant added, to B, and then when we go from B to somewhere up here, we'll call this point C, where we have sort of, we've gone to the other side of the equivalence point. So let's look at the region of A to B, so between A and the equivalence point. Okay, so at this point, we should think about what's going on with our reaction. Well, we've added in some base, but we haven't gotten to the equivalence point. So if you look, in this region, our excess reagent is going to be HCl, and our limiting reagent is going to equal the NaOH. So if that's true, and that makes sense because we haven't reached the equivalence point yet, so we're always going to, before the equivalence point, we're always going to have less NaOH than we're going to have HCl. We're basically working our way up to that amount of HCl. So if this is the case, if our excess reagent is an acid and our limiting reagent is a base, it makes sense that our pH is less than 7 because we have acid around. So that's what's going on in this region of A to B. We have an excess of HCl. We haven't reached the equivalence point. We're adding in NaOH, but we haven't gotten it all the way up to the amount of HCl we have. And so therefore we have excess HCl hanging around and our pH is going to be 7. And you can see that mathematically here. So if we do this one out, in this case where we're in the region of A to B, all of our NaOH is going to go away. That's going to give us 0 moles. We're going to subtract 0.2 moles from our HCl, which is going to give us 0.8 moles. So we have HCl hanging around, and we're going to have 0.2 moles of NaCl. And because that's neutral, that's not going to affect the pH of the solution. Now, what's going to be interesting is when we do this with a weak acid, because when we do it with a weak acid, that is not going to be true. So we're going to have to take into consideration the fact that the reaction is producing conjugate base in that case. But for strong acid, strong base, the fact that we're making NaCl really doesn't do anything because those are just spectator ions. And so it makes sense that our pH is less than 7 because we have an excess of acid hanging around. So we're kind of working our way through here and going up. And now what's happening is as we get closer and closer, our number of moles of HCl are going down, and the number of moles of NaOH is coming up to meet that. And so what's going to happen is eventually, as we get sort of to this range, we're getting so close to where we have an equivalence, meaning we're basically adding a strong base to something that's a very, very, very low concentration of acid, that the pH starts to change really, really rapidly because there's no more acid around to counteract that base, or there's very little acid around to counteract that base. So this rapid rise that takes place here is because as we reach the equivalence point, the relative amounts of acid and base are quite small in the solution, and therefore when we add the base, it makes a big, big effect on the pH. So that's why we get the rapid rise near the equivalence point. Now let's look at from A to C. So this is going to be the case where we're past the equivalence point. And so we're going to be adding in, so let's kind of retool our stoichiometric table here. So in this case, we're somewhere past the equivalence point. And so our moles of NaOH are going to have to be greater than 1 mole. So in this case, let's say we have 1.5 moles of NaOH. So we've added more than the 1 mole of HCl, and now what's going to happen is, and so our excess reagent is going to equal the NaOH, and our limiting reagent is going to equal the HCl. So it makes sense in this case that if we have extra base around, that our pH is going to go above 7. And we can prove that mathematically. So in this case, what we're going to get is we're going to have our limiting reagent is going to become the HCl. So this is going to be minus 1 mole. So we're going to have no acid around. We're going to have minus 1 mole. So this is going to give us 0.5 moles of base hanging around. And we're still going to have 1.0 moles of the NaCl that's made. But again, that 1.0 moles of the NaCl, that's just spectator. That doesn't really care what's going on. So all that we have in the solution that's going to affect the pH is this excess NaOH, which is going to make us be basic. And so this is how you can interpret a strong acid, strong base titration curve. So what we're going to do now is we're actually going to go in and we're going to look at an example of this where we're going to do some calculations. Okay, so on this slide, we have a strong acid, strong base titration curve, and this sort of summarizes what we were talking about before. So you can see this is actual data. This is real data where we have 50 mils of a 1 molar solution of HCl, and we're titrating it with 1 molar NaOH. So in this particular instance, we know everything, and that's going to be for demonstrative purposes. So in this case, what you can see is in region A, we have HCl as our excess reagent. Our limiting reagent is NaOH, so our pH is less than 7. And so our H3O plus concentration is going to be the moles of HCl minus the moles of NaOH divided by the total volume. And we're going to look at that in just a second. Then we reach our equivalence point, and at this point we have our moles of HCl equal to moles of NaOH. So our solution is going to contain just NaCl and H2O. And so therefore the pH is going to be 7. And then we talked about what happens when we get to past that equivalence point, we get to the region where the NaOH becomes an excess, and so our pH is going to be greater than 7. So let's look at some calculations here. So we have the 0 volume of pH added, and we can see that basically at that point, so at this point right here where we have 0 volume of NaOH added, what we basically have is our beaker sitting there with our 50 mils of the 1.0 molar solution of HCl. And so at this point, we can say that our pH is going to equal the negative log of 1.00 molar, which is going to equal 0. So we can calculate our pH there, because at this point where we've added no base, we haven't done anything with the base, we just have our acid sitting there with a concentration of 1.0 molar, and so we can calculate the pH directly from there. Now let's look at this case where we have 40, 50, and 60 mils. So we're going to work these out. We're going to work these out on a clean sheet, and then we can come back and add those values in just a minute. Let's look at 40 mils, 50 mils, and 60 mils, and we're going to work those out. So the first thing we're going to do is we're going to figure out how many moles of HCl we have in the solution. And that's not going to change throughout this entire titration, because in essence, the 50 mils of the 1 molar is always going to be 50 mils of the 1 molar. What's going to be changing is the number of moles of NaOH that we've added in. So if we take our 0.050 liters times 1.0 molar, this gives us 0.050 moles of HCl. And so now for each one of these examples, we'll figure out how many moles of the NaOH we've added. So for moles of NaOH for 40, this is going to equal 0.040 liters times 1 molar, which is our concentration of NaOH. And so we're going to have 0.040 moles of NaOH added. So let's set up our reaction. HCl plus NaOH goes to H2O plus NaCl. And so in this case, we have 0.050 moles of the HCl, and we have 0.040 moles of the NaOH. So at this point, I can identify that I'm not at the equivalence point because the two are different, and I can see that I'm going to be in the first region. So my limiting reagent here is going to be the NaOH, because there's less of it, and I have 0 moles of NaCl to start. Okay, so we're going to subtract away the 0.040 moles. That's going to give us 0 moles. We're going to subtract away the 0.040 moles. That's going to give us 0.010 moles of acid that's left over. And just to be sure that I do all of my math, I have 0.040 moles of the NaCl that's being made. But again, for strong acid, strong base, we're not so worried about that because that's neutral. So that's not going to do anything. So if I want to get my pH in this case, that's going to be equal to my concentration of H3O+, negative log of my concentration of H3O+. So to get my concentration of H3O+, this is going to equal 0.010 moles, which is my moles of HCl, divided by the volume, and that's going to be a total of 90 mils. So I have my 50 mils of the acid that was there plus my 40 mils of the base. So this is 0.090 liters. And what this gives me is a concentration equal to 0.111 molar. And so my pH, if I take the negative log of that, is going to be equal to 0.95. And so that makes sense because I have an excess of HCl, my pH is going to be less than 7. Okay, so let's look at what happens when we do 50 mils. So in this case, my moles of NaOH at 50 mils is going to equal 0.050 liters times 1.0 molar, which is going to give me 0.050 moles of the NaOH. So if I do my stoichiometry table, and what I'm going to do is I'm going to set this all up. I'm just not going to write my reaction again. So I'm just going to set this up as a stoichiometry table using the same reaction above. So in this case, I have 0.050 molar and 0.050 molar. So I recognize that I am at the equivalence point here. So, and I have 0 moles of the NaCl to start. So when I do this, I'm going to subtract away my limiting reagent, which in this case I don't have one because they're the same. So I get 0 moles of the acid and 0 moles of the base, and I get 0.050 moles of the NaCl. Now, because NaCl is neutral, and I just have water and NaCl around, that means that my pH is going to equal 7. I don't have any extra acid or base around to change my pH. So now let's look at the final case where our mole, where we've added 60 mils. So in this case, I have 0.060 liters times 1.0 molar is equal to 0.060 moles. And so if I set up my stoichiometry table, it's going to turn out that my limiting reagent in this case is going to be the acid. And so I subtract the 0.050 moles away. So I get 0 moles of acid, and I get 0.010 moles of base. And I'm going to also get 0.050 moles of the NaCl, but that doesn't matter because it's neutral. And so now if I want to get my pH in this case, I have to get my concentration of H3O+, but I don't have any H3O+ in there. I only have the NaOH that I can work with. So what I can calculate here is I can calculate a concentration of OH-, which is going to equal 0.010 moles of the OH- divided by the total volume, which I have to remember that it's 50 mils plus my 60 mils. So this is going to be a total of 110 mils, and that's my 60 mils of base added plus the 50 mils of acid that I had to start. And so this gives me a concentration of OH- equal to 0.091 molar. So I can get a pOH from that by taking the negative log, which is equal to 1.04. And if I convert that to a pH by subtracting it from 14, I get 12.96. And so when I get my excess of base, it turns the pH basic. And so that's how I get that. So now you can see the 3 main points along a strong acid, strong base titration curve, how to do the calculations. It all boils down to these limiting reagent tables. And then to get the pH or the pOH, it's just a matter of getting the number of moles and dividing by the volume for a strong acid, strong base. The key thing is to understand, though, that when you reach the equivalence point, the pH is 7, because I have neither acid nor base around. The only thing I have in solution is a neutral salt, and so that makes the pH 7.